Good evening, ladies and gentlemen. Dr. John Belkowitz here. We're going to be working on our PMXDB Practice Mix Design book. Practice Mix Design number 4, and we're working on a mix for Caissons. So, I want to apologize in advance. Kids might be coming in, but let's get to work. So we're working with a Caisson mix. This is our groundwork here. We've got a drill into the ground. We're going to auger out a certain amount of soil, and then we're going to replace that soil with concrete, pumping out any water. That'll harden up, and then we can go ahead and put our foundation over this and then, design from there. This is going to be, we got a slump of 6 inches. We got a 28-day. This is going to be 4,500 PSI. We want to design for 1 cubic yard. Coarse ag is going to be absorption of 1.0%. That moisture of 1.3%. We got a specific gravity of 2.62, and then we got a dry rotted unit weight 99.3 pounds per cubic foot, and also we're dealing with a river rock. Okay, fine ag, we got an FM of 2.92, specific gravity of 2.61, and we have an absorption of 1.2. It's a high absorption, and a moisture content of 5.8%. All right, so we are going to use ACI 211. I have that off screen here. We're going to start with table 6.3.1. So step 1, our slump from table 6.3.1 is going to be, well, it doesn't matter because they give us a 6-inch slump. In the ACI, they have it listed as a 3-inch slump. And what we could do is we could design for this and then slump it up using a high range water reducer here. Okay, so that's number 1. So we're going to do with a 3-inch slump. And if we go with our coarse aggregate, oh, I forgot to add, I'm so sorry. This was a MSA of 1 inch. Okay, so our next table, we're going to go item number 2, and this is table 6.3.3. And we can use a NonAir Entrained concrete for this. And I don't believe that was written on here, but we are going to do a NonAir Entrained mix. Whew. So if we do a NonAir Entrained mix at a 3-inch slump with a maximum sized aggregate, so design water for NonAir Entrained is 325 pounds per cubic yard. But because we have rounded aggregate, we're going to pull out minus 30 pounds per cubic yard to give us 295 pounds per cubic yard. And please bear in mind, this is for NonAir Entrained concrete, and this portion right here comes from the note underneath the table at 6.3.3. And our air for this, since a NonAir Entrained concrete, we're at 1.5%. Okay, so now we're going to go to step number 4, which is table 6.3.4a. And NonAir Entrained concrete, let me get my calculator. It says to use somewhere between a 0.48 for a 5,000 PSI and a 0.47 for 4,000 PSI. So we'll take the average. So we're going to do a water cement ratio of 0.525. And we do our check in table 6.3.4b. Specimens, all structures wetted continuously, freezing and thawing. Nope, none of that stuff. So we can use this 0.525, and I'm going to end up using a 0.52. Okay, so with that, let's go ahead and determine our cement content. So weight of water over weight of cement equals 0.52 equals, I know I have 295 pounds per cubic yard, and then I need my cement, and of course that's going to equal 295 divided by 0.52. So we end off with 567 pounds per cubic yard of cement. So a final thing we're going to do here using the tables is determine our coarse aggregate. So our coarse ag, pounds per cubic yard, equals, what is our finest modulus? 2.92. And we have a 1 inch aggregate. So we're going to use from our table 6.3.6, 0.66, and I determined that from my MSA, my maximum size aggregate, which is 1 inch, my finest modulus is 2.92, which my 0.66 is like really right on the line between 2.8 and 3.0. So I'm going to take my 0.66, I'm going to multiply that by my 99.3 pounds per cubic foot, and then I multiply that by 27 cubic feet per cubic yard. Gives us 770 pounds per cubic yard of our coarse aggregate. So what I'm going to do to keep track of all of that, I'm going to put another little box over here. I'm going to say weight in pounds per cubic yard, and we've got our water, which is equal to 295, our cement, which is equal to, and this is pound per cubic yard, and then this is equal to 567 pound per cubic yard. Our coarse ag is equal to 770 pound per cubic yard, and then our air content is equal to 1.5%. Now the reason why I wrote this off to the side is because I'm going to erase all of this stuff. And remember, design for a 6 inch slump. So it looks like we've got everything here. I'm going to go ahead and erase this stuff on the left and get to my other calculations. So let's go ahead. So what I've done is I've used the tables that are provided in ACI 211 to determine, the values that I just shared with y'all. Now what I want to do is take those values, determine how many cubic feet I'm using up out of my cubic yard, which you don't remember, we have 27 cubic, 27 cubic feet per cubic yard. So I'm going to design for that, and this is really the parameter I'm going to stick to. So the first thing I'm going to work with is my water. Now I have 295 pounds per cubic yard. Now what I want to determine is cubic feet per cubic yard, and to do that I have to divide by my unit weight of water, which is 62.4 pounds per cubic foot. Gives me a cubic feet of 4.73. Put a little asterisk. The next thing I'm going to do is my cement. Now I remember I had 567 pounds per cubic yard of cement. I want to divide that, not just my unit weight of water, but I also have to multiply by my specific gravity of my cement. Now you can go ahead and look this up. I'll go ahead and give that to you. That's 3.15. And in doing so, that gives us a unit weight of 196.6. So if I take 567 divided by 196.6, my cubic feet in cement is 2.88 cubic feet. Okay. So now, put an asterisk by that. I'm going to do my coarse aggregate. Let's do air. Air's easier. So my air content was 1.5%. Now this is a lot easier to do than all the others. All I'm going to do is multiply by 27 cubic feet per cubic yard, because again, 1.5% of my volume is air. So we'll rewrite air. 1.5 divided by 100 times 27 is 0.41 cubic feet. Okay, so then we go to our coarse aggregate. We're almost done here, folks. And we had 770 pounds per cubic yard, and of course I'm going to divide that again And this time I've got to use the specific gravity for my coarse aggregate, which was 2.62. And in doing so, gives you 10.83 cubic feet. And I'm going to rewrite that right now. Now if I add all that together, 10.83 plus 0.41 plus 2.88 plus 4.73, it gives me 18.85 cubic feet per cubic yard. But remember, I only have 27 cubic feet per cubic yard to play with. So I've subtract 27 minus 18.85 cubic feet per cubic yard. That equals 8.15 cubic feet. And that 8.15 cubic feet is all the room I have left for my sand. So let me go ahead and do one more set of math problems here. So fine aggregate, and I need to find pound per cubic yard, and I'm left with 8.15 cubic feet. I know my density of water, which is 62.4 pounds per cubic feet, and then they give us our specific gravity of our sand, which is 2.61. So if we multiply all that jazz together, 8.15 times 62.4 times 2.61 gives us 1,327 pounds per cubic yard. We're going to round that down to 325 pounds per cubic yard. And add that to our list, fine aggregate equals, it was 1327, but we're going to round it to 1325 pounds per cubic yard. Okay, good. So now what we need to do is take into account our moistures and absorptions, and then do a calculation for our high range water reducer, and then we should be good to go. Okay, so we know all our weights. We got our sand content. Now what we need to do is determine how much more weight we have to add because of our moisture from our rock and our sand. So let's go ahead. So coarse ag, and we'll say wet, pound per cubic yard equals 1770 pounds per cubic yard times 1 plus our moisture, which is 1.3% over 100. That equals 793 pounds per cubic yard. Our fine aggregate, wet, pound per cubic yard equals, what was that, 1325 pound per cubic yard, and our moisture on that was 5.8%. So 5.8 divided by 100, and we got 1402 pounds per cubic yard. All right, so now we've got our new weights, and let me go ahead and write these right here. And again, we're doing that because these ags are bringing some moisture with them. So if they're bringing moisture with them, they're laden with moisture, that means they're going to be heavier than the calculations that we already did with a bone-dry state. So now what we're going to do is calculate the amount of batch water. So batch water is design water, which in our case was 295 pounds per cubic yard, minus the water that we get from the rock and the sand. And when we look at an aggregate, you have two types of water. You have water that's been absorbed into the body, and that's based on our absorption number. And then you have a certain amount of free water on the surface of the aggregate, and that's going to be moisture minus absorption. And the reason why we're concerned about that is that moisture is going to contribute to our mix design, our water cementitious ratio, as well as our water of convenience. So we want to take that water into account. So with that, we got to subtract our water from our rock and sand. So let's go ahead and do that. So that's going to equal 295 pound per cubic yard minus, and the first thing I'm going to do is my coarse aggregate. So I take my 770 times my moisture, which was 1.3%, minus my absorption, which was 1.0%, and of course all of that divided by 100. And so this was our coarse ag, and of course we're also going to have plus our fine ag, and that was 325, and this is pounds per cubic yard. 325 times 5.8% minus 1.2%, all divided by 100, gives us a new water content of 228.74 pounds per cubic yard. So let me do a new water of 228 point, we'll just say 229, we'll round that up. Okay, so let me write our final mix design here. Okay, let me write this final mix design in a cubic yard basis, then I'll do the high range water reducer and we'll call it good for tonight, folks. So our final mix design is 1 cubic yard batch for Caissons. So our water was 229 pounds per cubic yard. Our cement was, or is, 567 pounds per cubic yard. Our coarse ag, moisture laden, is going to be 793 pounds per cubic yard. Our fine ag is 1,402 pounds per cubic yard. Now, bear in mind, this is all for a slump of 3 inches. And that's because we designed it using ACI 211. Now, ACI 211 does not take into account high-range water reducers. So we've got to do that ourselves. So bearing that in mind, most high-range water reducers, and you don't necessarily have to use a high-range water reducer. The reason why I want to use a high-range water reducer here is because we want to design for a much higher slump. We're going from a 3 to a 6, and we can use a mid-range or a normal water reducer, but the tendency to get us up to a 6-inch slump, we might have to use a much higher dosage. And in that, we can cause some effects that we just don't want to have with our concrete mix design, especially if we want to get on top of those caissons in a few days. So for my high-range water reducer, and there's a bunch of them out there, and really it's the back of the soup can, but let's just assume that my dosage rate to get me from a 3-inch slump to a 6-inch slump is somewhere around 4.00 fluid ounces per cement hundredweight. Now, what the heck is a cement hundredweight? I mean, that's something that took me a long time to really understand, and really all it is, so we have our fluid ounces per hundredweight. We're going to multiply it by our 567 pounds per cubic yard of cement by 100. So that means if we have 567 pounds per cubic yard of total cementitious and we divide it by 100, that means we have 5.67 hundredweights of cement. And when we multiply that through 4 times 5.67, we end up with a high range dosage per the truck. It's really 22.68, but we can go ahead and round that up to 23 fluid ounces per cubic yard. And like I said, cubic yard. So like I said, most of these high range water reducers back of the soup can. So really just identify that, look at the manufacturer's recommendations, and then go from there. And please bear in mind, let me go ahead and rewrite this. Please bear in mind that You know, everything that we do here, these are not the final mixes. These are just benchmarks. This is what we call bookcrete. And what we want to do from here is all good concrete practices dictate that we try our mixes out before we go out to the field. So we take this bookcrete and we tailor it, we dial it in the lab, and that's called labcrete. And once we get that dialed in, making sure we're hitting our slumps as well as our strengths, we go for our real crete where we dial it in into the plant. So hopefully this helped you out. Let me know if you have any concrete questions, concrete concerns. Don't forget to like and subscribe. Go concrete, beat asphalt.